Hello everybody and welcome to our third lesson in Unit 3 on quadratic functions. Today we will perform operations on complex numbers and you will learn what complex numbers are. You will express the results in simplest form using patterns of the powers of I, and we will identify field properties that are valid for the complex numbers. If we go back and think about how we find the roots or solutions of quadratic equations, let's look at these two examples. The left example has the equation f of x is equal to x squared minus 1. If we want to find the solutions or zeros, we have to take the left side and set it equal to 0. Y is equal to 0 at our solutions, right? In order to solve this equation, we're going to add 1 on both sides. So then we get 1 is equal to x squared. Take the square root of both sides of the equation, and our solutions are positive and negative 1 is equal to x. Please always remember that when we take the square root of a number, we have to have a positive and a negative solution. Think about it. If you take positive 1 and multiply it by itself, the answer is 1. If you take negative 1 and multiply it by itself, the answer is also positive 1. So remember, always a positive and a negative solution. Let's look at the example on the right. F of x is equal to x squared plus 1 this time. Setting f of x equal to 0, we get 0 is equal to x squared plus 1. Need to subtract 1 on both sides. Then we get negative 1 is equal to x squared. Take the square root of both sides. Uh-oh. And here you see you got the square root of negative 1. And up to this point, we have always said that there is no solution for the square root of a negative number. And indeed, there isn't a solution in the real number system. But today you will learn about a new number system, which is called the imaginary numbers. And the imaginary numbers are based on the following definition. I squared is equal to negative 1, which means that I is equal to the square root of negative 1. And with this new number system, we now have a way to simplify square root of negative numbers. And when we use imaginary numbers together with real numbers, we get something that's called complex numbers. And the complex numbers are usually written like this: a plus bi. And the a is the real part of that complex number, and the bi is the imaginary part of that complex number. So just to give you a few examples, 5 plus 2i is a complex number, but also 3 plus 0i can be written in a complex number format. Although if you look at it, you see there's no imaginary part. So this is really equal to just our well-known real number 3. And equally, you could write 0 plus 2i, which has no real number part and essentially is just an imaginary number, the imaginary number 2i. So let's take a look at how we can use this new number system of the imaginary numbers to simplify square roots of negative numbers. The square root of negative 128 can also be written as the square root of -1 times the square root of 128. So then, since we now know that the square root of -1, excuse me, is I, we can replace that by I. And now we only have to worry about simplifying the square root of 128. And 128, as you have already noticed, of course, is the same as the square root of 64 times the square root of 2. And we got I times 8 times the square root of 2. So by convention, we put the number first. So our final answer would be 8I times the square root of 2, which is the simplest form for our problem. Let's look at our next example. Then here we can equally say the square root of -1 times the square root of 7. The square root of -1 is I. Since we can't do anything with our square root of 7, this is as far as we can go. And our answer is I times the square root of 7. And let's look at our next example. Square root of -1 times the square root of 10 times the square root of 5. Square root of -1 is I, and the square root of 10 and the square root of 5 we can actually recombine to get I times the square root of 50, because wouldn't it be much nicer to split it up this way? I is equal to the I times the square root of 25 times the square root of 2, which is I times 5 times the square root of 2, putting the 5 in the front. This is our simplest form of this square root. See, I helps us a lot, and all we really do is we pull out the -1, make the rest of the numbers positive, and instead of the square root of -1, we just write I, and we're done. Pretty neat, isn't it? Now let's take a look at what happens when we take I and raise it to higher and higher powers. I to the first power is itself, of course, right? I squared, by definition, is -1. We talked about that. So let's think about what is I cubed then. I cubed is the same as I squared times I, right? Remember, adding the exponents, we get to the problem. I squared, we just said, is -1, and I is I. So in other words, I cubed is the same as saying -I. All right then. Let's look at I to the 4th power. I to the 4th power is I cubed times I. And I cubed, we just found out, is -I. -I times I is -I squared. And -I squared, since I squared is -1, -I squared is the negative of -1, in other words, +1. I to the 5th power can be split down into I to the 4th power times I. We already know that I to the 4th power is nothing else but the number 1. So 1 times I, which is equal to I. Let's keep going on a little bit. I to the 6th power is I to the 5th times I, which is I, because I to the 5th is I, times I, which is I squared. And I squared is, of course, -1. You have already seen a pattern, I'm sure, but let's keep going. I to the 6th power times I is equal to -1 times I, which is essentially negative I. And I to the 8th power is equal to I to the 7th times I, which in return is negative I times I. Negative I times I is negative I squared. And as we found out above, that's the negative of negative 1, which is 1. So as you can see, the results repeat themselves in patterns and in groups of 4. Every 4 powers go through the same sequence, and that continues on indefinitely in groups of 4. So if we now want to use this knowledge to figure out, for example, how can we simplify I to the 27th power? The way we do this is we need to figure out how many times does 4 go into 27. So dividing 4 into 27, we get 6, but we get a remainder of 3. And the remainder of 3 means that this is like I to the 3rd power. In other words, I to the 27th power is the same as I to the 3rd power, which is negative I. Alright? Now you can keep doing that, but when the numbers get higher, there's also a calculator tip that we can use. If you take your exponent and you divide it by 4 on the calculator, you're going to get one of 4 possible outcomes. You can have a number with a decimal of 0.25, and that is equivalent to a remainder of 1. And this means that you can simplify your power to just I. If you have a remainder of 0.5, a decimal of 0.5, that's equal to a remainder of 2. And the remainder of 2 means I squared, or in other words, negative 1. A decimal of 0.75, then you guessed it, is equivalent to a remainder of 3. And that means equivalent to negative I. And if you have no remainder and the number can be evenly divided by 4, that means you have just I to the 4th power, and I to the 4th power is the same as just the number 1. Let's look at an example. What if we had I to the 429th power? I'm just going to pull out my calculator, and I'm going to say 429 divided by 4, 107.25, and 0.25 means a remainder of 1, or in other words, this is just the same as I itself. Very well, guys. Now let's continue and watch the second part of this tutorial.